Le Chatelier's principle. Now, you may realize or recognize that some people pronounce it differently. I've always pronounced it Le Chatelier, so I will continue to pronounce it like that. But what is Le Chatelier's principle? Technically, we learn about it at GCSE. We learn it again, or we need to still know it for A level. Le Chatelier's principle is, if a system at dynamic equilibrium is disturbed by changing conditions, the position of equilibrium will move to counteract the change. You may realize in doing your revision that different exam boards use different phrases, different textbooks use different phrases, the internet has different phrases for Le Chatelier's principle. Just learn one, okay? The principles is the same. The process is the same. So just make sure that your explanation is giving all of that. Otherwise, you won't get the marks. But there are a few variations that are accepted by exam boards. So don't worry too much about it being word perfect, but make sure that you're saying all of the bits that need to be said. So you're talking about it being disturbed, the equilibrium being disturbed or put under stress, and that the position of equilibrium moves to counteract or reduce the change. Or reduce the stress, or whatever it is, whatever phrase you've used. So just pick one and learn it. Don't try and learn 4 or 5 different ones. Just pick one, learn it, and ignore the rest. So at constant temperature and pressure, if you're dealing with gases, Kc doesn't change. Kc does not change. So the pressure of equilibrium, the position of equilibrium will change in order to keep Kc constant. So you get Le Chatelier's principle happening, this process happening, in order to keep Kc the same. And I found it quite interesting, quite useful to think about it in that way. It's almost like reversing it. When I was learning about it, and now when I teach it, there's 2 ways to think about it. You can say that the position of equilibrium the position of equilibrium changes to adjust to a stress, or you can think about it in terms of Kc has to stay constant. If Kc has to stay constant, then something's got to change to make sure that Kc can stay constant. And that's what this position of equilibrium movement is doing. It's adjusting to keep Kc constant. Unless we change temperature, Kc stays constant. Yes, so there we go. If temperature changes, then Kc will change. The value of Kc will change, which means if the value of Kc has changed, the concentration of reactants versus products will change. If Kc is constant, the ratio of concentration versus, ratio of the concentration of reactants versus products, products versus reactants, sorry, because products are on the top. If Kc is staying constant, then that ratio must stay constant. So things will adjust to keep that ratio the same. Okay. Let's think about it visually then. So if you were a visual person, you might enjoy this diagram. I quite like it. We're going to come back to it though. We're going to think about what's happening first, and we're going to come back to this diagram. So let's say we've got a reaction in our laboratory and we increase the concentration of one of the reactants. Then it's going to, if it's in a dynamic equilibrium, it will react more. That reactant is going to react more, producing more products. We describe this as an equilibrium moving the direction of the products because we've had more of a reaction, more of the forwards reaction happening. Likewise, if we increase the concentration of one of the products, it will react more, producing more reactants. So the backwards reaction, will happen more. So we'll get more reactants produced. A consequence, therefore, if we think about it in the opposite, is if we remove a product from a system at equilibrium, the position of equilibrium will shift to produce more. That's where this diagram comes in. This whole diagram comes in. This is particularly useful in industry. This is used in industry to extract useful products. Sorry, I've just been told that my pen battery is now low, so I'll Just going to pop that into charge while I'm chatting. So I've always found it easier to think about it when you're in terms of when you're adding products in or you're adding reactants in, what's going to happen to the position of equilibrium. So if you're clear on that, you can use that principle to think about it in the reverse. If you were to remove a reactant or remove a product, the equilibrium would shift to replace the stuff that you've removed. And this is why we can use it in industry to extract useful products. We've got our reaction mixture prepared, this top left diagram up here. We leave it to reach equilibrium. It produces our darker blue products. And let's say this is nice and neatly 50-50, just to make it visually easier for us to see. So we've reached an equilibrium where there's a 50-50 mixture. That's where our position of equilibrium naturally sits. That's where Kc sits. If we extract some of the products, because we want to take them away and use them, however we do that, you know, put it through a separating column or whatever it is that we do, we extract some of our products. We're left with less products than we have reactants, and the ratio is off. So in order for Kc to remain constant, there must be, the position of equilibrium must shift to get us back to the point where Kc is constant. So the position of equilibrium shifts briefly to allow more reactants to become products to get Kc back to that position again. In doing so, we've used up more reactants again. So we've got more products. So we can then repeat the process. Remove some of those products, Kc will adjust. Sorry, the position of equilibrium will adjust to get Kc back to being where it was before. We've got more products again. We can extract them, etc., etc., etc. So really, really useful principle in industry for the production of useful products. Production and extraction of useful products. Okay. If we are thinking about it in terms of gases, though, things are a little bit different. Same as it was at GCSE, though, but we have to be able to explain it at A level. So increasing the pressure of a specific gas is equivalent to increasing its concentration. If you think about pressure in terms of particles per unit area, so the actual definition of pressure is the force of particles on certain areas, but the higher the pressure, the more particles they're going to be per unit area. It's equivalent to increasing the concentration. Let me see if I can get my pen back out again so I can use it. So changing pressure, changing the pressure will only affect reactions involving gaseous reactants products, obviously. Reactants. Hopefully I've left myself enough space involving gaseous reactants and or products. Because obviously we don't talk about pressure of solids or pressure of liquids. So only things that are have reactants and products in the gaseous state. Sorry, my writing's a bit rubbish there, so hopefully you can still read it. Changing the overall pressure of a system may therefore affect or may, however, affect the position of equilibrium. How? If we change the pressure of a reaction in equilibrium, how may the position of equilibrium be affected briefly? Do we think? So if we've got a system where the reactants, the number of moles of gaseous reactants in the reactants is different to the number of moles of gaseous products, this is going to affect our position of equilibrium. So changing the overall pressure may affect the position of equilibrium only if there are different numbers, so no's, I'm going to say numbers of moles of gaseous molecules on, or substances, actually I'm going to say not molecules, substances on either side of the balanced equation. Think about why that matters. Equation, we'll come to it in a second. Balance equate, that doesn't look like a word. Let's try that again. Equation. We can use Le Chatelier's principle to predict the change. Think about why it matters as well. Link it to your understanding of gases and volumes of gases. Think about why it matters. So, for a system at dynamic equilibrium, if the overall pressure is increased, what happens to the gaseous molecules? If we increase the pressure, so we go from a lower pressure to a higher pressure, let's say we double the pressure, what happens to the gaseous molecules in terms of their interactions with each other? We get more collisions. They will collide more. Let's make that a word. Collide more. This is an increase in pressure because we've got more collisions. That means the position of equilibrium will move to favour the reaction where our particles are going to collide less. We're going to favour the direction, so products or reactants, which produces the fewer total moles of gas, So let's give an example. This is the same example we looked at before, briefly, when we were looking at KC. We've got 1 mole of gaseous reactants on the left-hand side, and we've got 2 moles of gaseous products on the right. If we increase the pressure then, our system is going to favour the side with fewer moles of gas. This will reduce the pressure again. How do we know this? What principle does this come from? This comes from this idea that we learn that 1 mole of an ideal gas will take up 24 decimeters cubed of space. 2 moles will take up twice that space if it's at room temperature and pressure, if allowed to do so at room temperature and pressure. So the more moles of gas you have, the more space they are trying to take up, and therefore the higher the pressure. So more moles of gas equals higher pressure. So if we've increased the pressure, and it's trying to decrease the pressure again, Le Chatelier's system is trying to decrease the pressure again, it's going to move to the side with fewer moles of gas to reduce that pressure again. Not release, reduce that pressure. So what have we got here? We've got 1 mole on the left-hand side. We've got 2 moles in total on the right-hand side. So fewer moles are favoured at higher pressure. Favoured at higher pressures, or let's say higher pressures, and more moles are favoured at lower pressure because they're going to try to expand to fill the space. So you want more moles trying to take up space if you lower the pressure. So this is favoured at lower. Write that again. Lower pressures. Hopefully everyone is happy with that and can determine that sort of thing. When you come to do an exam question, I think we're about to do one, think about the phrases that you're going to use to explain it.